Hi, my name is Selma, and this is the third and the last video in the critical section problem series that I'm making. I'm going to leave the link to the playlist in the description, and I'm also going to leave timestamps in case you want to jump to a certain part of the video. In this video, I'm going to talk about Peterson solution, which is another software solution for the critical section problem. As I just said, it's a software solution, meaning that it's a set of instructions or code that you write. You don't have to change anything in the hardware of your computer to use the solution. Also, in Peterson solution, our two processes will still have to take turns, like in strict alternation, but the alternation this time is not strict. To understand this more, let's look at an example. I'm still using the donuts example I've been using in the last two videos. Basically, in this example, we have two processes. Process 0 eats donuts and process 1 makes donuts. They both have a shared memory location where the number of donuts are kept. So basically, process 0 reads the number of donuts in the shared memory location. It subtracts from this number, and then it updates back the remaining number of donuts to the shared memory location. Process 1 reads the number of donuts from the shared memory location, adds to this number, and then updates the new number of donuts to the shared memory location. So let's say process 0 starts first. It's going to eat 2 donuts, which means that it's going to subtract 2 from the 10, giving us 8, and then it's going to update the shared memory location. So now the 10 becomes 8. Now technically it's process 1's turn, and process 1 is interested in making donuts, so it makes 6 donuts and it updates the shared memory location with 14. Next, it's supposed to be process 0's turn, but let's say process 0 is not interested in eating any more donuts, and process 1 is interested in making more donuts. So that's the thing about Peterson's solution. Peterson's solution will allow process 1 to take a turn without having to wait for process 0 to take a turn. And that is the key difference in Peterson's solution, is that it takes in account if the process is, as we say, interested. So for example, here process 1 is interested in making 6 more donuts, so it's going to read the shared memory location at 6 and then update the shared memory location back. So in this case, the final number of donuts is going to be 20. But how does Peterson's solution do that? How does it check if a process, as we say, interested or not interested? Let's check out the coding example to understand more. This example has two main variables. The first one is an integer called turn, and the second one is an array of Boolean, and it's called flag. It has two elements, and they are set to false. This Boolean array has very important usage in Peterson's solution, and it's responsible for the whole interested thing we've been talking about. Okay, so here I have two methods. The first one is called intersection, and the second one is called leave section. Now, the code that's on the internet might not have these two methods, but it's just basically the same thing. That's the way I learned it, and I think it's just easier to break down the code. Okay, so intersection method takes in an integer, and that's the process number. In our case, it's either 0 or 1. In the method, there is an integer called other, and it's basically the other process number. So for example, if we have process number 0 is trying to enter the critical section, the other process is going to be 1 minus 0, which is going to give us 1. Oops, there is a typo here. Okay, so in this case, other is equal to 1. If the process number is 1, then other is going to be 1 minus 1, which is going to give us 0. So after we find the other process number, we set the flag at the index of the process number to true. So what does this mean? This means that this process is interested, this process wants to enter its critical section. And then after that, we set the turn into the process number which wants to enter its critical section. And here is the interesting part. We've seen this part before in the strict alternation code, the while loop with nobody. So this while loop just keeps checking the conditions, and if the conditions are true, it just sits there doing nothing, and that's what we call busy waiting. Okay, so the first condition it has is that if the turn is equal to the process number, which is true given the last line of code, The second condition is that it checks if the flag of the other process is equal to true. If this condition is true, this means that the other process was interested in entering its own critical section, and this means that the other process is currently in its critical section. If not, then this while loop is going to break, and then our process is now ready to enter its own critical section. After the process is done with its own critical section, it calls the leave section method and it gives it its process number. This method changes the flag into false. This means that the process is no longer in its critical section and it's done, it's not interested until it changes the flag again into true. Okay, so let's try to apply the donuts example into this code. So we said that process 0 is going to start us off by eating 2 donuts. It's going to call the intersection method and give it 0. And inside the method, other is going to be set to 1. And flag of 0 is going to be set to true. And finally, the turn is going to be set to 0. Next is going to go to the while loop. So the first condition of the while loop is true because turn is equal to 0, but the second one is false because the flag of the other process, which is flag of index 1, is still false. We haven't changed it and process 1 is not interested yet in taking a turn. This means that the while loop is going to break and now process 0 is ready to enter its critical section, which is eating 2 donuts and accessing the shared memory location, of course. But let's say that while process 0 is in its own critical section, process 1 tries to enter its own critical section, meaning that process 1 tries to call the intersection method and passes in its process number, which is 1. So in this case, other is going to be equal 0, flag of 1 is going to be set to true, and turn is going to be equal 1. So now let's look at the while loop. So the first condition of the while loop is true because the process number is equal to 1 and turn is equal to 1. And the second condition is also true because other right now is equal to 0 and the flag at index 0 is equal to true. And that is because process 0 is still in its critical section and it has never changed the flag at its index back to false. This means that the condition of the while loop is true, and this gives us busy waiting. This means that this loop is going to sit there and wait until the conditions are no longer true. In the meantime, process 0 gets back after being preempted from its critical section. It subtracts 2 from the 10, which gives us 8, and it updates the shared memory location. After that, it calls the leave section method, and it gives it 0, which is the process number. So the leave section is going to change the flag at index 0 into false. And this means that process 0 is no longer in its critical section and that process 1 is free to enter its critical section. So if you go back to the conditions of the while loop, now condition 2 is no longer true. Flag 0 is now false, so the condition is not true. So the while loop breaks, and now process 1 is ready to enter its critical section. It does. It enters its critical section and makes 6 donuts. So it adds 6 to the 8 in the shared memory location, and it updates it back, which means that now the shared memory location has 14. Next, it calls the leave section method and it passes in 1, which is the process number. This method changes the flag at index 1 into false. This means that process 1 is no longer in its critical section and it's not accessing the shared memory location. Now, since we say that the alternation is not strict, say that process 1 wants to take another turn and wants to make donuts, so it calls the intersection method, gives it 1, so other is going to be set to 0, and flag at 1 is going to be set to true, and turn is going to be set to 1. And let's say it doesn't get preempted this time and it enters its critical section. Everything's going smooth. So it accesses the shared memory location and it adds 6 to the donuts. Let's take this out. We no longer need it. So it adds 14 plus 6, which gives us 20, and then it updates the shared memory location. After this, it calls the leave section method and passes in 1, which changes the flag at 1 into false. So this is basically the difference between Peterson solution and strict alternation is the flags part. And this flags part is why the alternation in Peterson solution is not strict. Now let's summarize Peterson's solution by looking at some of its pros and cons. As I just said, one of the very good things about Peterson's solution is that it doesn't require strict alternation. Another thing is that it follows all the rules of mutual exclusion, and the most important one of them is that a process is prevented from entering its critical section only when the reason is that another process is in its own critical section. And the one con worth mentioning is still busy waiting. That is all what I have for mutual exclusion and mutual exclusion solutions. Thank you so much for watching. Please like the video and subscribe to the channel for the newest videos to reach you. Thank you so much.